I'm really happy to introduce Martha White today. Martha's assistant professor in computer science here. She did her PhD work at University of Alberta and got the PhD in 2014. And she has a lot of awards and accolades to her name. She has a Best Dissertation Award. She recently got NSF CRII Award, ICMLR Best Paper Award, I think. And momentarily she's going to make history as our first repeat speaker in the entire history, the entire 16-month history of the Intelligent Systems Seminar. So, really happy that you've earned this. And that's right, good. Really looking forward to your talk.
Okay, great. My name is Martha White, like David just told you, and many of you here already know me. And today I'd like to tell you a little bit about some new results on learning representations with dictionary learning. And I'm really excited about these results. These results are very new. I'm really excited to tell you about them. So let me tell you a little bit about what setting I'm looking at when it comes to machine learning. So I can kind of start getting a feel of what kinds of algorithms I'm looking at and why I care about those algorithms particularly. So the setting I'm typically looking at, one second. Okay, apparently this is not playing. 1 second, I'll probably have to. There we go. So the setting I'm typically looking at is the setting where we have this constant stream of data, and you like to make predictions about that data. So here, for example, I've just plotted something like wind speed. You can imagine the setting where you don't just have one scalar series of data, you just get a constant stream of lots of different information. And in such a setting, we like to do prediction, where we might want to predict what's the immediate outcome going to happen on, say, this step or next step. Or for something like a time series setting where you might want to ask what's going to happen long-term into the future. So what might happen in 10 steps from now, what might be a cumulative outcome into the future. So for these kinds of general prediction problems, I'm generally imagining I'm in this setting where I always have more and more data, lots and lots of data. So I'd like to have efficient computation, and I'd like to have algorithms that can incrementally learn on this data. All right, so as part of this, I'm going to have a very standard machine learning setting, but again, keeping in mind this world that I'd like to do prediction in. We're going to have some kind of raw input sensor information, and we call this our vector X. This could be things like I just showed you wind speed, or it could be other pieces of information about the environment, like the humidity, system status, and so on. And I'd like to use all this information to then make predictions about some outcomes. And I've already told you the types of outcomes I might care about, say some kind of immediate outcomes or long-term outcomes about the future. So generically, I'm just going to talk about these things as X and Y from now on, and I'm going to assume you know what kinds of X and Y I might care about. For these types of prediction problems, we're typically going to have pretty complicated functions. We're going to have some complicated function from our sensory information X to whatever our target variable Y might look like. So these are going to be nonlinear functions of our inputs. So to actually learn these nonlinear functions, the strategy I would like to take is representation learning. My goal is going to be to take this input information X, transform it with some nonlinear transformation phi, that's going to be our new representation, and then we might just do some kind of simpler learning algorithms on top of that transform representation. So here I'm going to be caring about this representation phi that transforms our X, and then we might just do a standard linear learning where we're going to learn these weights W to try to predict whatever target that we care about. Okay, so that phi is that thing that I really care about. So this phi is going to take whatever d-dimensional inputs we have. This d-dimensional vector might contain things like wind speed, pressure, and so on. And it's going to produce some new k-dimensional vector that is our new representation. Very simple setting. So that's really what representation learning is going to be about. It's going to be about learning this feature vector phi, or learning this function phi. So once we learn this nonlinear transformation, we're going to have a lot more power to actually predict these interesting targets Y. So generically, I'm looking at something that looks like this. We have some input vector. Let's say here this 4-dimensional input vector. We have some transformation here to produce our new phi. And then once we have this new phi, we're going to go ahead and do linear learning. Or some kind of simplified learning, maybe with some kind of signal transfer there. Okay, so that is what I'm defining is representation learning. The word representation learning is used in a lot of different fields, and this is really specifically what I mean about representation learning. Okay, and so as you can imagine, for such a general problem, there's lots of different strategies. And there's lots of different strategies I've been looking at for representation learning. And these are some of the main strategies I've been looking at. Things like adaptive kernel representations, predictive representations, which is a little less frequently used in machine learning. And what I'm going to talk to you more about today is dictionary learning. So some of the stuff I've been doing with dictionary learning. So before I tell you about dictionary learning, I'd like to give you an idea of what kinds of properties I'd like to have from this representation that we're going to learn. So really there's two different dimensions of what you might want from a representation learning approach. There is how useful is it for prediction, and what are its learning properties. So I'm going to try to focus on both of these things. So first, for the utility properties. The main goal that I'm going to have is I'd like to have more accurate predictions. But there are, of course, other goals you might care about as well. Maybe you don't care as much about having extremely accurate predictions. Maybe you want to learn faster. So you want to learn representations that will let you learn way fewer samples. You might have other stability properties that you'd like to have. You'd like to make sure that your representation ensures that across many different samples, you're actually going to see similar models that are learned. So when it comes to utility, there could be lots of different properties that you could define. The one I'm really going to focus on most is I want to learn representations that are going to make me make more accurate predictions. So as part of this, I'm going to try to make this case to you that to obtain this property, we really want this representation to be informed by its prediction utility. So I'm going to make sure we design objectives that are always learning our representation so that it's adjusting based on how well it's actually making us predict, as opposed to maybe some more of these unsupervised learning objectives for representation learning. Okay, and then on the other axis, we also care a lot about what are the learning properties of our representation learning approach. So you might have a really great way to do representation learning, but it's extremely expensive or only theoretical because there's no way you can run it in practice. So we're also going to want to ask questions about how can we learn these representations with the strategy that we picked. So again, because I told you what the setting I really care about, these are really the properties that I'd like to have for representation learning. I want to make sure that we can learn our representation incrementally. I really want to make sure that we can do this efficiently. Another goal is going to be that we have actually principled estimation algorithms. So I want to make sure that when we specify the representation learning approach, we really know that we're actually going to get optimal solutions for that representation learning approach. And then we can say something about what our representation is. And of course, always I want my algorithms to be used by people, so I really want them to be easy to use. So I have a preference here for simplicity. So you have a general idea of what I'd like to get out of representation learning. So now let me tell you a little bit about work towards getting these types of representations with dictionary learning. And I'm going to kind of spin a little bit of a picture here for you where we started dictionary learning and start moving towards a more interesting model. But nonetheless, I'll give you the takeaway at the front, at the beginning, so you can see where the story is going, and then I'm going to reveal to you how the story has actually gone along. So I like the story towards how we end up at something that looks a lot like a supervised autoencoder, but start off at something that's a little bit simpler with dictionary learning. So the takeaway for most of the rest of this talk is going to be that we can get a really effective representation learning approach with a simple supervised autoencoder model. And the way that we actually get to such a model is by starting first with dictionary learning, generalizing a little bit of stuff with dictionary learning, and by starting from dictionary learning, we're actually going to be able to get a model that gives us principled estimation, gives us really nice optimization techniques, and we actually get some really nice prediction performance at the end. So this is going to be the main takeaway from the talk. Okay, so now let me get more into the meat of things. So I'm going to go through and explain to you exactly what dictionary learning is and what a supervised autoencoder is, and I'll give you some results at the end. Okay, dictionary learning. So many of you here maybe have heard of dictionary learning before, but I'm going to start right from the beginning. So in dictionary learning, this is really a very general approach used in machine learning for unsupervised learning. So for learning representation, but learning it in an unsupervised way. So here we might again have our inputs x. Again, let's just imagine they're four-dimensional vector. This is for one sample x, and we're going to try to extract this new representation h. Before I was calling it phi of x, but now I'm going to need a concrete variable. So I'm going to call that h. It's going to be our hidden representation, and our goal is going to be to try to recreate our inputs x with the multiplication of our new dictionary and our representation h. So our dictionary D is going to be composed of many different atoms that could feasibly re-represent our input data. So we're going to hope that the dictionary has many useful representative atoms, and then H is just going to be able to linearly weight whatever atoms it finds useful to recreate our X. So the generic optimization for this is just assume you have some loss that says how similar is d times h to our x, so how large is your reconstruction error. Some regularization on h that tries to encode some properties on h, and also some regularization on d to encode properties on d. So I'll give you some examples of what these look like. So here, for example, if you might have some set of dictionary atoms that have been given to you, I'll try not to neglect this out of you too much, then you might have an optimization that looks a little bit something like this. So in this case, your reconstruction error would be minimize your square distances between x and d times h. And you might also want to have some kind of L1 regularizer on h that is going to enforce sparsity. So I'm not going to give you justification right now about why the L1 regularizer actually enforces sparsity. But by solving this optimization for h, it's going to try to set as many elements in h to 0 as possible. It's going to give us a sparse representation. This is just one of the nice properties of L1. Okay, another objective that you might have is something like a cross entropy. So you don't just have to use a squared loss between our inputs x and our reconstruction d times h. You might also use other loss functions. So here, if your x was say between 0 and 1, then you could use something like a sigmoid of d times h, and you'd use the cross entropy in that case. So you're going to try to minimize the cross entropy where you're looking at the sigmoid of d times h compared to the x that you have. Okay, and then this is another regularizer that you might use. You don't just have to use, say, the L1, you can use an L2, which is just going to try to keep the values small. So these are just two examples of many different options you can pick for this loss function, for the reconstruction error, and for the regularizers itself, although they are two very common choices. Okay, so this is still kind of abstract, but let me give you a bit more of a pictorial idea of why this type of approach is interesting at all, and why we can kind of think of it as representation learning. Because right now it's really just a way to factorize x into two values. But I think sparse coding is a nice example of why this can be thought of as representation learning and why it's interesting. Okay, so this is specifically a picture from a project about looking at brain data with a collaborator here named Franco. And what they have is they have a bunch of images of the brain, they have diffusion information at different points in the brain, and they like to reconstruct that diffusion information based on different, we can imagine of things like fibers, or we call them fascicles, that go through different regions of the brain. So this diffusion information tells you something about how things are moving through that region of the brain. And if you have atoms that tell you, there could be something that's moving through that region at this angle with this shape and at this angle with this shape, then you could say that these two atoms, linearly weighted with some coefficients, do a pretty good job of recreating the diffusion information for that particular point in the brain. And you really didn't need to know anything. You didn't need to weight anything of, say, something going with this angle through that part of the brain, because you already got all the information you needed just from these two very useful atoms. So here you can imagine a dictionary with many, many different atoms that are useful for reconstructing this diffusion information. And then your H is just telling you only have coefficients on these two atoms, and everything else is going to be 0. Okay, now you can imagine if there was another X that looked pretty similar in terms of diffusion information, you would actually likely extract a very similar representation, maybe with coefficients that look a little bit different. So two X's that look somewhat similar are actually going to be mapped likely to two similar sparse representations. And now we're hoping that once we have a sparse representation, learning should be a little bit easier. Other examples of sparse coding are usually things with images, where we try to extract out different edges in an image and then weight different edge structures to try to recreate parts of your image. So this is a similar idea. Okay, so assuming that you have now extracted out this set of dictionary atoms, so we're going to want to learn a good set of dictionary atoms, and then we're going to want to extract ways that we're going to weight across those dictionary atoms. So just to make sure it's clear here, for this D times H, if you're a little bit rusty with your matrix vector multiplication, this D times H is always going to take this H, and it's going to multiply, it's going to turn sideways and multiply all the rows of D. So it's going to extract out by multiplying sideways here. Because most of H is 0, it's just going to end up selecting this column and this column, and it's going to zero out all the other columns when it does the matrix vector multiplication. Okay, so once you have this new representation, let's imagine you went ahead and you learned your dictionary atoms D and you extracted the right coefficients for all of your samples. Now we're going to have some new representations H1 all the way to Hn for our input samples X1 all the way to Xn. And then now we can just go ahead and do regular supervised learning, whatever supervised learning you'd like to do. So here we're going to learn some W times our new representation to then predict our targets Y. So examples, things like linear regression, logistic regression, or you could use really whatever supervised learning technique you like. I'm typically going to stick with simple ones, again, because of this whole principle of estimation approach. So do feel free to interrupt me at any time. So this would be a good time where hopefully you have an idea of how the dictionary learning approach extracts new representation and then allows us to do learning with a new representation. So a natural question then is, how are we going to do prediction on new data? That's always our goal. So we're going to do learning on some set, and now we'd like to know what is our target going to be on some new data we've never seen. So once we've done training, we obtain this set of dictionary atoms. Extracting the representation on a new data point is pretty simple. So we're just going to go ahead and install this optimization. We're going to try to find our H that best linearly weights all the dictionary atoms that we're saying are useful dictionary atoms. And then that still also matches the regularization properties we cared about. So if we want it to be sparse, we still want to make sure we use that sparse regularizer. So for some new X, we're going to extract our H, and then we can just do prediction with our W times H, where we learn W again on this training set. Simple. Everything should be simple still. Okay, so let me still tell you a little bit about how the algorithm works and how this satisfies some of the properties that I really would like to satisfy for representation learning, but how it's really missing some of the other ones that I care about. So I would like to tell you first about why I care about this approach. One of them is that we actually can do nice principled estimation for this model. And so that principled estimation is going to lead us to something that is actually both effective and has principled estimation. We're going to see for dictionary learning on its own is not particularly effective yet. But it does have something that's really nice about how we can actually estimate it well. So one thing you might notice is that this dictionary learning approach, we have to learn both this D and this H. So we have this biconvex optimization problem, but it's non-convex in both D and H. So whenever we have nice convex optimization problems, we can do gradient descent and we can get to an optimal solution, and we're happy. We specify our objective, we can get the optimal solution to our objective. So that's not the case here. It's not obvious exactly how we can get the optimal solution. But we do have some really nice results, actually with Leigh, who's sitting right here, about how we can optimally estimate these types of models. So even though it's non-convex, we're going to have this really nice property that we have found about these models. So here I'm going to introduce this term. It's called strict optimality property. So many of these dictionary learning models are going to have the strict optimality property, which is really two things that are very important. The first one is that all the local minima that you might have for your objective are actually global minima. So as long as you converge to a local minima, you know you've converged to a global minima. So that's already a pretty surprising result, but it's a very nice result. And then there's something else that's additionally really important for actually optimizing these models. So in addition to local minima, global minima, or local maxima and global maxima, there's all these stationary points that could be saddle points that are really the flag of non-convex optimization. So a large part of neural network research right now is how do we deal with these terrible saddle points that impact our optimization. So one of the nice things about this problem is that we do have saddle points. We know some settings where we have saddle points. But all of our saddle points satisfy this really nice property, which is that they are not degenerate saddle points. And so if you remember exactly what a saddle point looks like, it looks something like this, where you're at a point where your gradient is 0, but you're neither at a local minima nor at a local maxima. In some direction you could then further decrease, and in some direction you might actually increase. So for our optimization problems, a non-degenerate saddle point, so if we don't have degenerate saddle points, what that really means is that for all the saddle points that we have, there's always a reasonably clear direction where you could continue descending. So there's all these nice new results about gradient descent that show as long as you don't have degenerate saddle points, so as long as you have the strict saddle property, gradient descent is very unlikely to get stuck at those points, and you will converge to a stationary point that is a local minimum. So since we know from the second property that we're always going to converge to local minima, or very high probability going to converge to local minima, we come to our first part, and now we know we're always going to converge to global minima. which is really nice. So we can just use very standard gradient descent approaches. We're just going to do alternating minimization with these variables. We can take advantage of well-known approaches for stochastic gradient descent as well, and we can be pretty confident that we're going to reach our global solution. So I'd like to tell you, I guess, a little bit more about when is this true. This can't be true for all dictionary learning methods, and it's definitely not true for all dictionary learning methods. But there is a pretty nice general class of dictionary learning methods that this is true for. So particularly, there's this really nice way to identify which of these problems are likely to be easy. And so we've identified some set of problems that are likely to be easy, but this criterion, I think, could help identify other problems that could be easy that we haven't really thought of yet. So we're typically going to require these these two things. First, we're going to need to make sure that our loss function is actually convex. So this reconstruction error, where we're looking at our x hat to our x, so this d times h compared to our x, that really needs to be a convex function if we're going to be able to do anything with this. For our regularizers, we're going to have something of a specific structure where we can use mostly any kinds of regularization we'd like to on the columns of D, but really our regularizers have to be summing over regularizers on the columns of D and summing over regularizers on the rows of H. It may not be obvious why that is true, and I won't be able to explain it now, but you should go look at this paper if you'd like to know more about why it has to have this specific form. So we need to make sure that our regularizer on D and our regularizer on this H, make sure that has this type of form where we have any function that, as long as it's convex, non-negative, and centered, that our RD looks like that and our RH looks like that. So this matches a lot of the norms I showed you earlier, but it also allows you to do other types of regularizers that are not norms, which is pretty nice because most of these objectives have typically only considered norms before. Okay, so if you have these two properties, there's this nice outcome where if you look at this function, so this is a little bit of an ugly function. Let me tell you what it's saying. It's saying if you look at this regularizer on the actual reconstruction itself, so the d times h is our x hat. It's telling us how we're reconstructing our x. If we had instead our regularized function on top of this d times h, that's defined this way. So it's saying find the dk and the hk. That's exactly equal to our reconstruction d times h, but that is the best dk hk that you could have found according to our regularizers. Okay, so you have your d and h, but there's possibly a different dk and hk that would have better satisfied the properties of your regularization, but produces the exact same d times h. Okay. So again, even this, you don't fully have to exactly intuit why this would be important, but in the settings where we can actually say that this induced regularizer is convex, those are the settings that are actually going to be easy. So it's a little harder to say something exactly about this factored form of regularizer. But if we know that this RK is convex, then we can go through and we can apply a really nice technique where we first look at this new induced form. We say something about the global optimality of that induced form, and then we can relate the stationary points of the other form, this factored form here, to the stationary points of the induced form. So that's a general idea of how we can identify this optimality result. And I don't really want to go more into the proof, but again, check that paper if you'd like. So really the main insights from looking at this that we have found is that the theory is already pretty general, but there seems to be some nice settings to be able to extend it further. So there's a few things we notice in practice. One of the things is that this FC and FR don't really have to be convex, actually. It's somewhat surprising, actually. In practice, if they're almost convex, if they're a loss that looks just maybe a little bit bowed, then we're still going to find this global optimality happen. So alternating minimization is still going to bring us to global solutions. The theory also requires that this dimension, this inner dimension, or the number of atoms in D, is reasonably large. But again, in practice, we find that the theory is asking for too large of a K. We can really set K much, much smaller and still get these properties. So those are two real insights, that the theory covers a pretty broad class, but there's so much more to be done. There's so much more to identify in this space of possible objectives where we can actually get global solutions. There is also something else that's really nice, is that we did some experiments where we tried to go outside this class in a different type of way. So for example, we changed our regularizer, so now that we couple the columns of D, rather than regularizing the columns of D separately. That completely broke everything. We got stuck in local minima all over the place. So it does look like this the specific form where we identify that these problems are easy is really meaningful, but there is an opportunity to go a little bit beyond. Okay, so like I told you ahead of time, now we have a way to say that we have principled estimation approach, and since we are just going to do gradient descent, we can use pretty standard gradient descent algorithms. So I guess I don't have that much time, so I'm not going to spend too much time on the estimation approach, but really we're just going to do stochastic gradient descent approach. We're going to see a new sample, we're going to update our dictionary atoms. The update looks a little different than a regular stochastic gradient descent update. And because I don't have too much time, I won't describe it more. But it behaves a lot like a stochastic gradient descent update. You can use very similar step-size selection strategies. Okay, so let's pop back up the stack. We have a much more in-depth understanding maybe of dictionary learning now. We can come back and ask, does this actually satisfy all the properties I said ahead of time I'd like my representation learning approach to have? So you can learn incrementally. It's actually pretty efficient in terms of computation. Hopefully convinced you that it has that we have a principled estimation approach. I put a little bit of a half check mark here beside ease of use because it's not maybe as easy to use as some of the other representation learning approaches. It's not like a neural network where you get to just do a feed-forward pass. Here for each new sample, we do have to solve this optimization problem, which is maybe a little less easy than you might be used to. Still though, mostly a check mark on ease of use, I'd say. But really it's missing this key component that I think is very important, which is you really want to learn representations that are informed by how useful they are for prediction. So everything I showed you with dictionary learning was just look at your input data and try to find a way to reconstruct your input data. It said nothing about how useful that representation was for prediction. And so, as humans, we can make up things that we think are useful for representations. Sparsity seems to be useful, so let's do sparse coding. And there's nice wins with sparse coding. But really, I think we get a lot further for always making sure our representations are informed by how useful they are for prediction. Okay, so to get that last point that we don't have right now, I'm going to move to something called supervised dictionary learning. I'll tell you about some of the things we do in supervised dictionary learning. So the idea behind supervised dictionary learning is a pretty simple one, actually. It's saying instead of just optimizing this dictionary learning component that we had before, so reconstruction error with some regularizer on H, also jointly estimate the weights W that you're actually going to use to predict your target Y. So now when you solve your objective, you're not just learning D and H, you're also learning W at the same time. Because all of these are jointly estimated at the same time, your H is going to be pulled towards making the reconstruction error or the loss on Y better. So now this would be a supervised, we'd be actually informing representation in a supervised way. And here I was a nice little graphical model to understand what's happening. Here we still have this H that's going to recreate our inputs X. So we still have this D that's recreating our inputs X. And we also have this W that's predicting our outputs Y, our targets Y. So though I'm not going to justify fully here, you can still use the same theory. There's a little bit of adjustment. You can still use the same theory though to say that we can principally estimate this. We can get global solutions for D, W, and our H. But the biggest problem with moving to supervised dictionary learning and why it's not typically done is difficulty with out-of-sample prediction. So before I mentioned to you that we learn our dictionary atoms, we extract representation by solving a minimization. That's no longer going to work in this setting. And really the key reason is to look at the difference between these two optimizations. So before we trained with learning an H that got to actually see both an X with this dictionary atoms D, it had this weight W, and so when you extracted that H, you were actually extracting an H that got to see the targets Y. Of course, on the new data, you will not see the targets Y, so there's no way to extract an H that's well balanced to what your training loss actually looked like. So in practice, what you'll find is that this H that's extracted, say, only using this unsupervised model, looks very different from the H that you would extract if you were actually given the W and the Y that you have for your training data. So you'll be able to extract an H, there's no doubt about that, but that H just won't be very useful for prediction, and your W times H for prediction will do a pretty bad job of prediction. Okay, so there's some simple things that we try to do first before completely giving up on this strategy. This is one of the most common strategies actually for supervised, particularly for supervised nonlinear dimensional reduction, where they really do just use this strategy for extracting H. So a few things we tried are things like, rescaling these regularization parameters to try to balance these losses a little bit more. this second loss here is now missing this component. So you might imagine that your regularization parameter actually has to be a little bit larger or smaller. Here this would have been a larger value, so relatively this term would have been smaller. So here you might actually just scale down your regularization parameter to account for the fact that you're missing this huge chunk of the loss. Okay, none of these really naive strategies actually seem to help very much. So we're going to take a different strategy when it comes to actually solving this out-of-sample prediction problem. So we really want to do supervised dictionary learning. We know we can estimate it principally, and now we want to take advantage of this supervised component. So we're going to do something that's pretty straightforward, but really it's going to be an important way to do it. So the key here is the title of the slide. I really want to learn this forward model jointly. So we're going to try to predict or learn a function that's going to predict this h that we've learned using dictionary learning methods. So we already can think of this h as a nonlinear function of x. Whenever we're doing a minimization over h, that minimization over h you can think of as a nonlinear function. So there's really two things that we could try to do. One of the first things we could try to do is go ahead and learn with your supervised dictionary learning approach, and then try to learn some function from x to recreate our h. Another strategy we could do is to implicitly learn h. So there's going to be these two strategies we could do. Let me just give you an example of what these two things might look like. Okay, so here, for example, we'll still have our supervised dictionary learning approach. We're still learning our d, w, and our h. And now at the same time, or jointly, we'd like to also learn an f, say that is linearly going to weight your inputs x to produce your h. So I just told you that h is clearly a nonlinear function of x, but this is just a simple example of something that you could do to try to recreate this h. Okay, so then now you'd be jointly trying to both learn a model that predicts what that h is, but also use these nice dictionary learning approaches that try to make h have the properties that we wanted h to have in the first place for supervised dictionary learning. And of course, instead of just using this square loss, you could use other ways to try to learn this forward model. Right now, we've mostly been considering something that looks like this, in fact, because always coming back, it's one of the only ones we can estimate in a principled way. Okay, and then another thing you can do is you can actually realize that you can just completely cut out the middleman. Maybe we don't need to explicitly learn this h. Instead, everywhere where we used to have h, we're just going to replace it with an f times x. Okay, so before we had a d times h to recreate our x, and we had a w times h to create our y, or to predict our y. So we're going to replace h everywhere with an f times x. Now we have these three variables, and we still have this multiplication of variables that is making this optimization non-convex. But really here we're implicitly learning h. Implicitly set h to equal to f times x. So these are two objectives that we can consider. And at this point, just looking at these objectives, it might not really be clear exactly how this is related to other representation learning approaches. But let me show you more again in this graphical model so you can see how it's really related to something called supervised autoencoders, or semi-supervised autoencoders. Okay, so this is what our supervised dictionary learning approach looked like. We had our h, we're reconstructing our x, and we're reconstructing our y. Okay, so one thing we can notice is we didn't really have to draw it exactly this way. We really could have swung, a little hard to add, we could have swung all these arrows over to this side. And this model is exactly the same as the original model. I just drew all the x's on this side, and the y is shifted up. Okay, so our new model, this is still the original supervised dictionary learning model with all of both our inputs and our outputs all on the same side. A little different than you usually see for a neural network. And then once we have this h here, we can say, well, let's learn a forward model to then recreate that h. And here we can either explicitly try to train this h and then learn this forward model, or we can think of this a little bit more like a neural network and actually just directly learn a forward model f and learn these d and w at the same time. So we've gone from dictionary learning, supervised dictionary learning, and then we just brought ourselves all the way back to neural networks because it's so convenient to have this feed-forward strategy. Well, what I'm going to convince you of is that actually having swung this part around here, or having this dictionary learning component at the end, is going to make our prediction performance actually surprisingly better. It's going to give us a lot more power. So there's not a lot more to say about the principle of estimation. I can't show you here, but again, the same kinds of optimality results are going to be there. And again, we can do stochastic gradient descent to learn all these parameters, the F, D, and W. Okay, so we can come back to our questions. Does it satisfy all the properties that we wanted it to satisfy? We can learn incrementally. Again, we have efficient computation. We still have principal estimation. I'd say it's even easier to use now because once we learn this forward model, it's much easier to do prediction. We just have some inputs. We apply our forward model. And we both learned our W and our D, but when it comes to estimation, when it comes to prediction, we just need to apply our W to our F times X. And finally, we also have representations that is informed by the utility for prediction. Yes?
Is there a reason we are not regularizing the fields?
Good question. So you mean the D and the W?
W.
So you are right that throughout I haven't drawn all the regularizations on F, D, and W, but I'm going to assume everywhere that we're always regularizing. In all our experiments, we will be regularizing. It's just that it starts to get more and more complicated to write it. Too much math on the slide. Yeah.
So another question I had was, so if suppose your X is like really large dimensional, then it will give more importance on getting the X's right, and maybe we want to go down the Y's, just the little compromise. There's a compromise there. As soon as X gets like high dimensional, then you might do a very good job of estimating X, but not of Y.
It's a good question. And in fact, I would say that that's one of the best things about this model, is that right now, when you have these large hidden layers, it's too easy to estimate Y, especially if Y is smaller dimensional. It seems that adding this X, we actually make our estimation of Y a lot better. We extract a much better hidden representation H because it's constrained in the types of H that we pick. So you are right that if you chose, let's say, a really small hidden layer and you had a huge number of outputs X, then your performance is going to degrade. But as long as you're picking a reasonable selection, you're giving your hidden layers enough nodes that you can actually do a reasonable job, it does well. You can also do this thing where you put more weight on your prediction loss and you put less weight on the X. You can just think of it a little bit like a regularizer, and you can always tune down how much you regularize with your reconstruction error. We've tried that a little bit, but it actually didn't seem to have a lot of improvement. So right now we're just waiting them equal. And Andrew can always correct me if I'm wrong. Where was I going? Wait, did I go all the way back? Right, I went all the way back. Okay, so like I mentioned, we started dictionary learning, and we came back to something like a supervised autoencoder model. So I would like to ask some very specific questions about, why did it matter that we started a dictionary learning? Are we actually gaining something by having started a dictionary learning? And also, how well do we solve this other question that we had before, which is how do we solve out-of-sample prediction for supervised dictionary learning? So really, we have two questions. Was it useful to start dictionary learning to get this forward supervised dictionary learning model? And separately, do we actually solve the out-of-sample prediction problem for supervised dictionary learning, which is just a separate problem that people actually care about? So we kind of like to answer both of those questions. So these are some of the questions that we try to look at. What are our advantages of this model that we're proposing over other supervised learning approaches? What are our advantages over other out-of-sample prediction approaches for supervised dictionary learning? And then maybe some other particular choices. So we have a pretty simple model. We really only have a few regularization parameters we can change. We can change the size of this inner dimension. So we really have the opportunity to ask precisely how do these things exactly affect our output. So we're really carefully looking at how does the increase in K change our performance, and how does the performance change as we vary, say, these three regularization parameters. And we're actually seeing some pretty interesting structure. So I'm only going to show you a subset of results today because I know we only have so much time. But we ran some of these models on this data set. It's called the determining data set. It is a pretty small data set. It has 10 inputs and 11 outputs. So the goal is to classify speakers into some categories that I can't exactly remember, but maybe you could talk to Andrew to ask him about it. And there's about 1,000 samples. This is a little bit of a mimic of a larger data set called the TIMIT data set, which is one of the next data sets we'll be looking at. So let me explain to you what this bar chart is telling you. So here on the y-axis we have percent accuracy, and these are the different types of models that we compare it against. So our classification accuracy again is out of 11, and these two blue colors look very similar, but this taller bar is our algorithm, which is great. Okay. And so we're comparing first against this chunk of this block of algorithms, which are all dictionary learning approaches, and then these two algorithms, which are neural network or more standard supervised learning approaches. Okay, so for these three, so this one first is supervised dictionary learning. This is a naive approach to supervised dictionary learning, and this is standard dictionary learning. So this is the dictionary learning. If you just did this unsupervised learning first, extracted a representation, and then did regular supervised learning. So you can see it really doesn't have the prediction performance that we would like it to have. It seems really important to have this additional thing where we actually form a representation. Okay, these two things, this is a slightly different way to do supervised dictionary learning in an out-of-sample approach, where it actually tries to take the dictionary learned in a supervised way, and then for the new data, it tries to guess what the labels might be, optimize the H with guessed labels. So it actually does a little bit better of an approach than the naive supervised dictionary learning approach I described to you, where you just pretend that it's okay that you optimize in a completely unsupervised way to extract this H. So even when you do something a little bit more clever, it's still not really gaining us a lot for the out-of-sample prediction approaches. So we really do gain a lot compared to other out-of-sample prediction approaches. Okay, and then these two algorithms here, logistic regression is always a reasonable baseline. So logistic regression is doing actually pretty reasonably well with no dictionary learning or representation learning whatsoever. And this algorithm, this neural network, is the corresponding neural network to our neural network-like structure, but without the dictionary learning component. So keeping the same number, allowing to have the same number of hidden nodes, using exactly the same transfers, using this cross entropy at the end. Just adding the dictionary learning component actually gives you a big jump in performance. So it really seems very important to constrain this hidden layer with some kind of strategy to make it pick hidden layers that do a better job of generalization. Okay, we also, as a second step, we looked at what about adding some more complexity to our inputs. So we transformed all of our inputs with a radial basis transformation using Gaussian kernels. And we did a lot of fiddling to find a good transformation that actually allowed logistic regression to do a good job of prediction on this data set. So we expanded out our new representation with the radial basis transformation, and then we just went ahead and again applied our regular forward supervised dictionary learning model. So this is starting with more powerful input features rather than those simple raw 10 features that we started with before. So again, actually the conclusions are pretty similar. But actually, in some sense, they're even stronger. Here, we're using a forward neural network-like model, which should have more capability for prediction than the logistic regression model. Actually, does worse than logistic regression because it seemed pretty hard to actually tune the regularizers for this model. So we were really just not able to get it to match the performance of logistic regression until we added these dictionary learning on the end that really constrained the space of our hidden representation. There's a question. Go ahead.
So, I mean, I don't know that much about learning, so I don't know if this question makes sense, but why does the dictionary, why does constraining your hidden representation help? Besides performance, I guess. Like, you may have addressed that before, but I'm not clear about.
It's a good question. So the question was, why does constraining the representation help with the dictionary learning component? The main intuition we have here about why it's useful to constrain that is mostly for generalization and performance. So this optimization space is under constraint. There's many H's on your training data. Well, there's many F's that then produce H's that would do a good job of predicting your target's Y on your training data. And then amongst that huge space of possible values, we want to pick the H that's going to do the best on new data as much as possible. So to do that, a common thing in machine learning is to add some kind of regularization. Pick the simplest H, or pick the H that doesn't have too large of values in it. So here we're adding a new way of, say, trying to constrain with that space of H's. And amongst that H, we're saying you should also be able to do a reasonable job of reconstructing our X. And that really seems to shrink the space and help it do better in terms of generalization performance. Now, why those types of H's would be better in terms of generalization performance, I don't think I have actually a great answer for. It's true empirically. It makes intuitive sense that we're constraining our space, our search space, and picking H's that are good at predicting stuff that are all related to the task. You know, the X's and the Y's are related to each other in a lot of ways. But I don't have a more concrete answer than that. Okay, And so we have a few more results also on in terms of how does prediction performance change as we allow the inner dimension to increase, and how do all these regularization parameters affect our performance. But I'll just give you the conclusions for those results since I didn't feel like I have enough time to tell you those. So there's really two, I'd say, really interesting conclusions that we did not anticipate when we started working on these. And really the first thing when we started trying to optimize these models is that we were getting terrible performance, and we weren't really sure why. And one of the things we found is that it's really important to have different regularization parameters for these three different models. So for this F, D, and W, they're all serving very different purposes. In order to actually get them to learn something useful, they need to be able to have different regularization parameters. So the regularization parameter, if you can't remember, is the magnitude of weight we put on each regularization for each of those parameters. So if you had an L1 regularizer on H, there's a regularization parameter in front telling you how much you want to make sure that L1 is imposed on our H. So a common thing for a lot of these dictionary learning methods is really just to pick the same regularization weight for either pairs of these models or even all three of those models, and that significantly degrades performance. There's even more structure there that we're not exactly sure about yet, where there seems to be cases where we really need to make sure that our regularization on W is always less than our regularization on D. It seems a very strong pattern. So there's more to understand about actually how setting these regularization parameters for dictionary learning can really significantly impact performance. Another thing we found that was pretty interesting is that having a larger dimension always seemed to improve performance a little bit, and the regularizers then able to compensate for any kind of overfitting. So some of the other semi-supervised autoencoder approaches mostly didn't actually use any kind of regularization. They used whatever loss functions they would like, and then they constrained their inner dimension to be pretty small. So here it seems beneficial to take this idea from dictionary learning, where instead we allow K to be large, and then we allow our regularizers to impose structure. And then of course the two insights from before is that we can also port the estimation strategies from dictionary learning and say something principled about this representation learning approach, and that in general dictionary learning has more to inform when it comes to optimizing neural networks. We can really start bringing more ideas from that community to get better optimization for neural networks. So in general, this is kind of the question I want to leave you off of. So it's a question that we're really trying to ask right now. Is how far can we really go with a single hidden layer? We really propose one structure to try to get a nice hidden representation H. And there's definitely been other work that has also tried to ask this question. So there was a nice paper recently about trying to optimize just a single hidden layer neural network, and they were unable to get good performance. But if they trained a deep network and then instead they learned a single hidden layer neural network by using that deep network, essentially compressing it down into a single hidden layer neural network, that neural network now did a great job of performance. So they weren't able to directly train it, but they were able to extract it later in this two-stage approach. I think this is all coming towards some evidence of we can do a lot with these simpler structures. We just need to have a way to optimize them. We need a way to constrain our space to do a good job of extracting that. And so here we had really two suggestions for how to try to make single hidden layer neural networks more effective. And that was to use this reconstruction of our inputs and to use our regularizers in an effective, careful kind of a way. So some natural next steps are, how true is this? Is this actually true if we start moving to more complicated neural networks? So let's imagine if we now add another layer. Maybe we do a two-layer neural network. Is it still useful to have this dictionary learning layer on the last layer? So we can look at other neural network architectures and just add the dictionary learning or not add the dictionary learning and see how that impacts performance. Of course, there's lots of other dictionary learning approaches we could look at. We looked at very simple L2 regularizers because it was really the first place to start, but there's, of course, work to be done with looking at sparse coding on that last layer. All the results I showed you were only for implicitly learning H, and of course, looking at strategies for using an explicit H could lead to different results. And like I mentioned earlier, there's still a lot more to be done for the theory. So the theory is so restricted to a smaller class than is necessary. And it seems like we can encompass a lot more interesting settings by looking at a bit more of that. So thank you for your attention. Go ahead.
So, if I understand correctly, so the first layer is trying to re-represent the input points, right? In a model.
Okay, let me just go back to which picture you're talking about.
The one that does the transformation learns H for a value out of sample point.
Right, okay. So this part right here, right?
Right.
Yes.
So how does this compare with SVM? In a sense, because SVM also non-linear, if the data is non-linear, it tries to convert to a high dimensional space. So this is essentially also somewhat similar to that. So I'm just trying to compare.
It's a good question. So SVMs do a little bit of what I said at the end there, where they have this radial basis function transformation. The idea more for SVMs is that you first there's a difference between, I should say this differently, that there's the representation I introduced at the beginning is phi of x. Now there's a question, are you going to learn the representation or are you going to make a fixed transformation? For SVMs, they're typically assuming that someone has done some interesting fixed transformation to transform some new space phi of x. And now SVMs are going to learn in a clever way with this new phi of x. And that's where all this kernelization happens. But really, SVMs are also just solving a linear model on this fixed representation. And the idea behind SVMs is more about how do we add this maximum margin property. But it is still just trying to solve for this linear classifier with this fixed representation.
So this is more flexible in that sense.
In some sense, it's
For the new points especially.
okay. I would say it's more flexible in the sense that we can also take a fixed transformation and then further do learning with it, which is one of the things we did with the radial basis transformation. But we didn't do SVM learning on the end there. But for the classification we did, we just used logistic regression on the end.
Would there be any advantage of making this a multi-layered structure?
Right. So instead of just having this,
One H.
instead of having this structure, we just have one H. We had another one. So
Would
right
there
now
be any
we're
advantage?
right now we mostly only looked at making this layer non-linear and seeing it as an advantage to having first non-linearity here. We are just getting results back for this. It doesn't seem to actually be a lot of advantage. Maybe particularly because optimizing it's just a little harder than optimizing this thing, which you can optimize globally. But I have yet no answer to adding one more. I'm going to say though that I think it's going to be very useful.
But to guide another H layer, we are writing a dictionary for the second hidden as well as the X's, or would it be only for the
So here, learning a second hidden layer here, you're saying, would it only be for impacting learning these X's? So in this setting where we would add another layer, output would still be exactly like this. It's only directly impacting in some sense this hidden layer, but it is going to be back propagated and impact the next hidden layer over here. I really didn't answer your question. I really didn't understand your question.
I guess my question is, so now the second hidden layer would have not only the hidden representation, but also the dictionary layer for the first hidden.
Okay, I got your question. So are you asking, would each hidden layer that we add, would we also add connections to Y and X to make sure that it's also predicting the X and Y at every hidden layer?
Yes,
So you're
for
asking-
that.
There's only one structure that we're considering looking at, but we haven't done that.
So I think on your first slide you gave part of the validation of this kind of online learning time series prediction.
Right.
Like in the end, if this is like a feed-forward neural network, how is this particularly well suited for these kind of problems?
Okay, so for particularly the fact that we actually made it into something like a feed-forward neural network, it's very well suited for these problems, in the sense that a very standard, or the set of optimization strategy we use for something like this is just doing stochastic gradient descent. We can write down our stochastic gradient descent rule as we see new samples. We can always incorporate those new samples, and then we can make predictions in a pretty easy way. Maybe what you're asking is how does this work for time series or things like that? I think that's your question.
Basically, yeah. Because I mean, yeah. If I already have a ton of samples and optimize my network, then adding one or two more samples in the time series probably won't change that much. Which is okay, I guess.
So if I've had lots of samples and I've trained an amazing network and it's predicting really well, I guess that's not a big problem. I agree. But really in this setting that I'm imagining where you have this continual stream of data, in some sense I'm kind of imagining, well, it could be non-stationary, you do want your model to adapt. But I was thinking more along the lines of, since we always do have new data, we'd like to design algorithms that are amenable to incremental estimation, which is not immediately obvious for some of the dictionary learning methods.
That makes sense.
So in language tests, I think what people usually do is learn the representation, plug into like LSTM or just start the whole, like from the beginning to end, just learn everything. So what you're suggesting is maybe you can apply similar kind of joint learning for the unit tests. Do you expect to see better results?
From doing joint learning rather than doing it in a two-stage kind of a way.
Yeah.
I think there's two parts to what you said, that there are some strategies, let's say like deep autoencoders, where they just train that first, then they pass that off to some other neural network learning algorithm. And then I think the other thing you said is there's also joint strategies now where there's just, these big neural networks, they have a supervised learning prediction problem, they have enough samples, they just train it all together right from the get-go. But I'd say that those are two separate things. The first one is this dictionary learning-like approach that I try to justify a little bit, just doesn't work very well. So this is really that two-stage approach you described. It's a very simple two-stage approach. It's just one basic dictionary learning-like thing. It's not like a deep autoencoder or something. But that is one where you train first, and then you pass it off to some other learning algorithm. The second thing you described is a standard supervised learning model that just has our outputs y and our inputs x. And that's a little bit like this graph, this bar graph here. This is really trying to combine the two together. Take that unsupervised learning component and also supervised learning component and do it all together at the same time. And it, at least for this model, helps.
But for many cases, this performance is also a function of how much data I put in, right? So do you have insights into whether this pattern stays with the amount of data?
It is a great question. So one of the biggest limitation of this result so far is only that we've done a very thorough sweep on this small data set. So all we can say so far is that with this architecture we've looked at, with the sigmoidal transfer on this data set, this is the result that we're seeing. Now we're moving to more interesting data sets like CFAR and TIMID. So I'll be able to tell you later. But I can't tell you yet, I don't know. Although I will say that there has been some work on semi-supervised autoencoders that looks something like this model, and they ran it on big data sets, and they got nice performance. So there's hope. This is definitely not completely new. There are different models that look somewhat similar with a little bit of a different architecture. So there's hope.
So I have more like software questions. So
Sure.
I'm more like neural network engineer, and then deep learning paper is kind of crazy. Like, okay, if you initialize this weight as an identity matrix, performance goes really high or something like that. So I don't know. I mean, so I'm wondering, is there any like parameter tuning difficulties in this your proposed algorithm? Like, I think you mentioned about the regularizer is key. So like weight to regularization is kind of tricky or something.
Yes, that's true. So for all these results, we have 3 regularization parameters for this. If you go back to the variables that I'm looking at are, this is the difficulty with animations. The variables are with this F, these red lines, which are the D and the W, and they all have regularization parameters. So these 3 regularization parameters. So for our model, we can do cross-validation across some range of different regularization parameters and all the different possible combinations. The cross-validation approach picks really good parameters and does a good job. So in that sense, it's not too sensitive. It's not that we have to pick a really broad range. But you do have to do that cross-validation. We have found for some of these models that it is a lot harder to pick the regularization parameters and their performance is not as good. So not our models, actually other models. Some of the neural network models we've looked at have been harder.
So do you have some practical recommendation how to tune these regularizers? Or it really depends on the data set?
For ours, we have a very clear structure about how it should be set. But do I have a practical suggestion? I mean, I guess I have to give the same practical suggestion I always give. For your own problem, I recommend, before really even looking at the data, pick a reasonable range of parameters. Try not to do too much data snooping, and just go ahead and use the computation to actually carefully sweep your regularization parameters. That's really the only suggestion I can give.
All right. Okay, maybe one more question. I know Martha has to get off to class in a moment, so.
Just wondering, from a software engineering point of view, how easy it is to take your physical estimations and plug it in and make it pluggable into your framework?
Actually, I would say it's really easy because it's really just a gradient descent strategy. You just add some regularizers. So the heavy lifting went into proving that that was an okay thing to do. So it's the very first thing you would want to do, and then you have to step back and say, oh, maybe this is a bad idea, but it's not. It's a good idea.
All right, we should let you get off to class, I think. But thank you so much, and thanks everyone.